The function f is defined by f of x is e to the power of x multiplied by sine of x. Find the Maclaurin series for f of x up to and including x cubed. To find the Maclaurin series, we can use formula with derivatives. It is given in the data booklet, but also we can use given expansions for e to the power of x and sine x. These formulas are also given in a data booklet. So we can write that f of x is equal to 1 plus x squared over 2 plus x cubed over 6 and plus so on up to infinity. But since we need up to and including x cubed, we don't need x to the power of 4 or greater powers, and is multiplied by x minus x cubed over 6 and so on. And we need just open parentheses and take terms only up to and including x cubed. So 1 multiplied by x, it's x, and 1 multiplied by negative x cubed over 6, it's minus x cubed over 6. X multiplied by x, it's plus x squared. X multiplied by x cubed, x to the power of 4, not required. And x squared over 2 times x, it's plus x cubed over 2, and that's all. Other terms will be power of 4 greater, which is not required. Hence, we can simplify and finally write that it is equal to x plus x squared plus x cubed over 3 plus so on. And hence find an approximate value for a given integral, and we can see that e to the power of x squared times sine of x squared, it's actually the same function f, but for x squared instead of x. So we can write that e to the power of x squared times sine of x squared, and it's this expansion but for x squared instead of x. So we can write that it's x squared plus x to the power of 4 plus x to the power of 6 over 3 and so on. And hence we can easily integrate it and get that it is equal to integral from 0 to 1 x squared plus x, or actually it's approximately equal x to the power of 4 plus x to the power of 6 over 3 dx, and we can easily integrate it, and it's x cubed over 3 plus x to the power of 5 over 5 plus x to the power of 7 over 21, and limits from 0 to 1, which is equal to 1 over 3 plus 1 over 5 plus 1 over 21 minus 0, and finally it's 61 over 105. The next part of this question, the function g is defined by g of x is e to the power of x cosine of x, shows that g of x satisfies the equation. The second derivative of g is 2 multiplied by the first derivative of g minus g of x. So let's find the first and the second derivatives of g firstly. So derivative of g is equal to we can see that it's just a product rule. So e of x derivative is e of x times just cosine plus e of x derivative of cosine, which is negative sine, so it's minus e of x sine x. The second derivative is derivative of the first derivative, so derivative of this part, it's again e of x cosine x minus e of x sine x, and minus derivative of this part, so it's minus again product rule, it's e of x derivative e to the power of x and sine x, and minus e to the power of x, derivative of sine is cosine. We can simplify it, and it's negative 2 e to the power of x sine x. And now let's consider the right hand side, because it will be simpler to show that it is equal just to the left hand side. So 2 times the first derivative minus g of x is 2 multiplied by the first derivative e to the power of x cosine minus e to the power of x sine minus just function e to the power of x cosine, and we can see that it is equal to negative 2 e to the power of x sine, which is equal to the second derivative of g as required. Hence deduce that the fourth derivative is equal to a given expression. Hence implies that we should use the obtained result, and we should use the expression for the second derivative, and we can find the third and then the fourth derivatives of g. So to find the third derivative of g, we can just differentiate the expression for the second derivative, this one, and get that the third derivative of x is 2 times the second derivative minus the first derivative, and differentiate again to get the fourth derivative is 2 times the third derivative minus the second derivative as required. Next, using the result from C, finds the Maclaurin series for g of x. To find the Maclaurin series, we can use formula with derivatives. G of x is g of 0 plus the first derivative of 0 times x plus the second derivative of 0 x squared over 2 factorial plus the third derivative of 0 x cubed over 3 factorial, which is 6, plus the fourth derivative x to the power of 4 at 0 x to the power of 4 over 4 factorial, which is 24. And we need to find g of 0, the first, the second, the third, and the fourth derivatives of 0. So function of 0, we can see that it's just 1. The first derivative of 0, where is it? It's here. So we can see that it's 1 minus 0, it's 1. The second derivative of 0, it's this, it's negative 2. No, it's not negative 2, it's 0, because sine of 0 is 0. It's 0. The third derivative of 0 is equal to 2 times the second, it's 0 minus the first, it's 1, so it's negative 2. And the fourth derivative of 0 is 2 times the third, negative 2 minus the second, it's 0, so it's negative 4. And hence g of x becomes g of 0 1 plus 1x plus 0x squared plus negative 2 over 6, it's just minus 1/3 x cubed, and minus 4 over 24, which is minus 1 over 6 x to the power of 4. And hence or otherwise determine the value of a given limit. Hence implies we should use the obtained expansion, and otherwise implies we don't need to use this obtained expansion and use any other method. And what method can be used? Since limit is 0 over 0, it can be solved applying L'Hopital's rule. But since we obtained expansion for g of x, it can be easily found a given limit. So limit x tends to 0, e to the power of x cosine minus 1 minus x over x cubed is equal to, just substitute expansion, it's 1 plus x minus 1/3 x cubed minus 1 over 6 x to the power 4 minus 1 minus x over x cubed is equal to, it's 0 0, and it is equal to minus its limit negative 1/3 minus 1 over 6x and other higher powers of x. And just substitute 0 for x, we get that it's minus 1 over 3, and each term, all other terms in this series will be equal to 0. Hence, limit is just negative 1/3. And that's all for this question.